Okay, so we should start. The first, notebook that I want to discuss is Schrödinger equation, solving the Schrödinger equation. In most of the course of quantum programming, we don't need to worry about solving Schrödinger equation. We just assume there are gates that are implemented, but the gates are implemented via Schrödinger equation. So basically, how it evolved, the system evolved, is according to this equation. Okay, so this notebook, we'll set up a Schrödinger equation in QuTiP and solve it. So this will use QuTiP SE solve. This is a Schrödinger equation solver. Okay. Yeah, so you import plot, you import NumPy, you import QuTiP, and from QuTiP you also import block sphere, quantum object, Q object evolution. Basis SE solve, sigma 1, sigma z, maybe also sigma x. So so we have seen how to make a block sphere. So this is a wave function, 2-level, and I guess unit is probably to make it norm to be 1. Okay, you have block, and then add states, and then show that. Let's see. Yeah. So this only works for 2-level system. You can see any error message if you use more than 2 systems. Okay, let's say we have this basis 3, 0, and 3, 1. And then it would complain. There's no, you cannot do that for expectation sigma x, y, z. So you have to have that. And then let's try by not giving it the unit. So you see it goes beyond the unit sphere. This, the error is too big. Even if you just use 1, this error is too big. And I have no idea why it shows twice. Let's see if I remove this. Yeah, I have no idea why it shows twice. Okay, now you have a magnetic field, and it's in the z direction. So that means this spin will precess respect to this magnetic field. Okay, let me just give the proper wave function. Okay, we have to that and that unit. So you set up the Hamiltonian, which is sigma z, and you have a time you want to solve, and you use Schrödinger equation solver, right? Hamiltonian, initial state, time steps, and this expectation operator that you want to evaluate. And as I mentioned, in the newer version, you will need to use these E underline OPS equal to the list of operator you want to evaluate. Okay. So this was solved. And then it says this the result dot expect. Just how do I close that? Accidentally open this. How do I close it? Should be a cross button, or maybe it's blocked by some control. Okay. So it says this is a two-dimensional array where the first dimension refer to different expectation operator that we need. We passed this, and okay. We can always print out. Just print out the result. A two-dimensional array. So 0. We should say expect. There's a two. And size is not defined. List. So this is a list. So this is the length. One. Oh, yeah. So this is inside the array. I thought you could just use size, right? Okay, this is a shape. Size is not defined. Okay, this is we have the shape, which is 100. This list of 100. So basically, that's the expectation value of sigma y. Right? We could put sigma x. It was not imported, but let's just say sigma z. Oh, one. Okay. So you give the array. The first array is the sigma y, and the second array is sigma z. Sigma z doesn't change because basically it comes in with the Hamiltonian. Okay. You can plot this. Okay, so yeah, in the above, we gave sigma y as an operator to Schrodinger equation solver directly calculate. If you pass an empty list, and you will return the quantum state. So this illustrated here, you don't pass any operator, and then you add the state. You add the state to to the block function, and then you show, so they give all the states on the block subfield. And so, as I said, it's probably in the future you will need to use this. So we just pass this, use the keyword. And yeah, I don't know why it shows twice. Okay. So yeah, last time we have the animation. So we can import this flood animation. Okay. And you also, once you have the state, you can evaluate that. So we import the expect function. And this was from previous notebook. There's an animation. This previous notebook. This one. You set up the plot and now the block sphere, and then can give you these animation. So that's what I paste here. And I have to evaluate these points. So the results, okay, the results are shown. Results. That states, oh, it's empty. Oh, because this is RES. Then give the state. And I have to remove things because I didn't store. I compute the points along the way. So I to add a trace, you have to plot these. Like previously, you have this. You do the animation, right? It traces out this. So here I take that out. I only add the vectors because I have to evaluate. Of course, you could calculate everything and then do the tracing. Okay. So to plot setup, you need to have these two functions. I guess one can improve and then maybe make it pre-calculate these results. Yeah, I'm sure you could do that. But I just simply copy and then remove things that does not work directly. Like here, the result already calculated the expectation value of 0, 1, 2. We could also do that. Then this code would work exactly. Okay, so this only moving the arrow does not show the trace. Okay. Next, we want to solve a field which can change in time. So yeah, the above we have a constant field, constant Hamiltonian. And to solve time-dependent field, you will need to, okay, these are represented by Q object eval in QuTiP. So we can define a magnetic field with a linear and a periodic strength. So two different ones. So there's a linear strength, time, return this 0.3, periodic, return cosine 0.5 times t. We can define this Hamiltonian linear in time, right? Which would be sigma z in the z direction, and linear is the coefficient. And this periodic is the cosine. So previously here, we just set up the Hamiltonian, just say H equal to the operator. In order to pass the time dependence, you will create these two functions, linear and periodic. So, and then pass that as part of the parameter to this Q object evolve, eval, Q object eval, okay? And to solve, that is just the same comment. This Hamiltonian, linear, and initial state, the time, evaluate sigma y. Okay, then you plot the result, sigma y. And again, this complaint about the keyword. So we just fix that. Okay, so this is for the linear ramp, and this is for the periodic. Right, and you see the response, and it's like, it's not periodic in terms of the cosine. Okay, so that's the notebook for the spin moving in a magnetic field. This is called Lamor-precession. Okay. Next one. It's all uploaded to the right space. Next one is Qubit-Dynamics, single qubit. This is the simplest system. Okay, so load the usual package. Like this time we have this ME solve. So we can solve things that are described, equation described by the master equation. So maybe it would be useful to point you to the documentation. I just search QuTiP documentation. User guide, evolution. So this is the physics behind that. So this is the Schrödinger equation, which is a unitary. We have seen things like that. And non-unitary evolution basically described as a system coupled to the environment, and you trace out the environment. So you write the system evolution totally involved as cell, but with the influence of the environment described as setup operator, jump operator. This is still unitary. It's describing everything, but if you trace out the environment, you're left with, so this is tracing out, you're left with a part which describes the unitary by the system itself and this jump operator, set of jump operator, C. Yeah, here is called collapse operator. These are operator that the environment act feedback to the system. And there are strength square root Rn are the rate. Okay, so yeah, of course it's not a course for this theory, but you can You found it in several places. Yeah, usually in the standard quantum optics books, or you can find in Newton Trump in chapter 6 or 7. Okay, so there are some assumed approximation, like you assume initially the system is not entangled with an environment is in the product state. And there's some approximation. The state of the environment does not significantly change as a result of the interaction with the system. So this environment is a big reservoir. The system and the environment remain separable throughout the evolution. So this may not be valid because there might be still, as you evolve, you couple the system to the environment, there will be entanglement that are developed. But it says it's justified with a very weak interaction. Yeah, and also assuming there's no memory effect, it's called Markov approximation. The time scale of decay for the environment is much shorter than the smallest time scale of the system. This approximation is short memory environment. The environmental correlation function decay is a time scale fast compared to those of system. There's also other thing, exact approximation. Element in mass equation corresponding to transition frequency. Like you have maybe levels that you make transition. This transition frequency. These transition frequencies certify that the difference is smaller than one of this system time. All fast rotating turn in the interaction picture can be neglected. Also ignore terms that leads to small renormalization of the system energy level. Yeah, this function is not strictly necessary for all master organisms. So there are other. This is called block. This is typo. This is HELCH block field mass equation. We'll see that. We will not see how they operate. We will see the result, and they can compare. Okay, so this is required for arriving at the limb block form. Okay. Yeah, so the example, we can see the example. So as you expect, if you don't have coupling to the environment, a single qubit with external field, you will see oscillation, perfect oscillation. With coupling to the environment, you expect to see decay. So this one. Okay, so the system here is the simplest one. As we already saw, it's with a energy difference between two level. This could be an external field, for example, in the previous case, in the Lamor-precession. And now we add a collapse or jump operator that describes dissipation of energy from qubit to an external environment. The collapse is defined. This is more of a dephasing. Oh, sorry. Here, no, this is the X direction. So this is like, yeah, relaxation. Okay. So this could be in the if you use this as Z direction, this will be sigma X. So it constantly flipping the environment is act in a way that would flip the system up to down, down to up. Okay, so we're setting up, this is the energy delta. G is this the rate or the strength of the environment. Okay, you set up this, and these are collapse operators. So that's why they use C up square root of G times sigma C, and it start with a stay in 0, and it's timeless. To solve this is the same as previously, but you use ME solve the master equation and Hamiltonian initial state time list, and additionally you need to have the collapse operator. EPOS is what you want to evaluate. Okay, you solve this, and because this is a simple system, you can solve analytically. So they provide this analytic expression, and compared to that, you plot the results, you plot the analytic. Okay, and it seems very, very accurate. Yeah, Qubit-Dynamics blocks here. So now the Hamiltonian is sigma z and sigma x. So they are still in the xz direction with angle theta. Okay. Here we pass an empty list of class operator, meaning that now it's real unitary dynamics. Okay, as we have seen, we need to use this keyword. So this is a visualization. You extract the expectation value for Pauli matrices. Sx, Sy, Sz is from the result from this expect. So you can print this. Result that expect. You see, there are 3 arrays, as we've seen previously. There's sigma x, there's sigma y, and sigma d. So this just assign to these 3, and then they just turn this into a NumPy array. And then you plot that, you add point, you add state, so the point will be showing these dots, and you add the state will show the error. Yeah. Here does not use the animation. You could have do that. So I wonder if we don't convert that into a NumPy array, what would happen? It does not affect because it's already array. So I think this part is not needed. Don't necessarily need to convert the arrays. And now you can compare the difference if you have dephasing sigma z. So you set that collapse operator. This is the square root of array times sigma z. And you saw it's basically the same. Now you have this C operator, which is no longer an empty list. And you have these expectation value. What is the keyword? It's like EPS something. EOPS. EOPS. Expectation of operators. Okay. Right. So we don't need to really convert, but you can do that. That's block sphere and add point, add state. Side 0 is the initial. So just add the error for the initial and then show the trajectory. And again, I don't know why it shows this twice. Okay, so this is for the dephasing. When you see the actually it going inside the sphere, it's no longer on the surface. And if we consider relaxation, like Qubit from the ecstatic state up can decay to down using the sigma minus. Okay, the setup is the same, so let me not going through that line by line. This is the keywords. Okay, so you see there's a difference. And if you want, you can also plot these expectation value using this. For example, we can compare this is result and you have expectation as x phasing. Okay. And there are relax. So we can maybe plot something circle SX. Is called times list. There are others like circular phase. Calculate and phase. How do we put a label? Let's see. You don't put labels. Let's see what we had previously. This probably does not have a label. Because no, this is label, right? Label equal. As you can see, I don't memorize it, at least. If I need it, I just search. Why it does not show up here? Legend. This is how we learn. I hope this is correct. There's no axis, so how do we add legend? Maybe plot legend. Okay, yeah. You can see, of course, this unitary one is that does not have a decay. Dephase sigma x is decay to 0 and relax. It will decay to the negative value. You can also see the y. Maybe that I would suspect y would be similar. Let's try to get some y is actually different. So why they all like decay, the two dephasing and relaxation, they all decay to 0. So we start with 0 here. Let's compare z. But even for such a simple system, right? You add dephasing, relaxation, it's hard to understand like intuitively. So this is how maybe we experiment with this numerically, and then you can get some intuition and see the plot. Dephasing. So the sigma z, perhaps it looks like it's going down to 0. And sigma z is going to really negative. Sigma y is going to 0 for the green. the green sigma x is also very negative. So at the end, it will be in the xz axis very negative. So that's what you see here. This is the relax. So this is hard to see. Maybe can we rotate this? No, we cannot move this. This one is for dephasing. For dephasing, the x go to 0, 0. It's here, yeah. So the x-axis, so x goes to 0, so it's close to YZ plane, but let's see what about y and z. X go towards 0, y also go towards 0. So x, y, z go towards 0, so it's toward the center, moving toward the center. It's not quite there yet. Right, so you have the tool to examine this. And you see this z is oscillating, and y have a lot larger amplitude, go from negative to positive, and x is also not quite for amplitude. This is because we have a field. H is along some direction, right? This is the direction of the field and the center of this circle. So you're moving like that. So you see x is changing, y is changing, z is changing, right? And for the dephasing, the changing is similar, but then it's getting shrinking and smaller and smaller. But this relaxation somehow is going down. Okay, so this is how we get intuition from running simulation, and yeah. Yeah, don't ignore this single qubit. The single qubit is really a good play to learn the intuition. Like if you have 2 qubit, it's already hard to visualize 3 qubit, right? Okay. So I don't expect I can cover everything that I uploaded. So I will let you explore the rest if I have not finished, but I would like to leave like 20 minutes for you to feel the course evaluation. Yeah, so the next one is Rabi-Oscillation. This one is qubit and the field. So there's these annihilation operator, creation operator, tensor product. So this is the Hamiltonian. You see the harmonic oscillator in the maybe last class or few classes before and in the last semester. This is the qubit, and this is the interaction. Basically, it's an electric field interact with the spin that make transition. And there's some approximation you can make. For example, you drop some cross term because this A dagger and then sigma plus somehow you create a photon and also move your level up. That's not physical, so you can drop that. So you're left with this. This will be the equation we're going to use. And there are jump operator. For example, C1 is you annihilate photons. So you annihilate photon, which corresponding to you raise this level of your qubit because you cannot solve. This is a thermal state. We talk about that. It's n+1. And this is to create photon is emission process. This is emission and square n. And then this is also the relaxation for the qubit. This already is complicated enough, but it has a lot of physics there. So you set up these parameters, coupling. You can read this. So this, for example, this kappa is this kappa here. That's the cavity loss rate. Gamma is atom dissipation rate. In thermal, you set some temperature. This setting 0 is the like in a 0 temperature. There's no thermal photon. Okay, so use rotating wave approximation. This is called rotating wave. Okay, setting up and also time and the initial state. It's in so you have n photons. So n is capped at 15, so it's from 0 to 14. It's for the photons. And the qubit is at zero state. And this is the annihilation operator. This is yeah, so you need to write in a tensor product because the qubit operator's identity, and this is for the sigma minor. So photon operator is at identity, and this is destroy using the destroy dagger. But you could just use sigma minus. You could just use sigma minus for the package. Yeah, then use sigma z here. Okay, if you have a rotating wave approximation, you drop cross term, else you have to include everything. Okay. Well, we're choosing the first Hamiltonian. Yeah, collapse operator. Use have the rate, photon annihilation, and then have that square root that times a, and then you have creation. Right, and add to the operator list, and then you also have the atom relaxation, decay. So you add that to that. So essentially, you don't need to know how to solve it. So really, basically, this is a quick way to learn. You learn the equation, okay? You know that's there. What term the meaning is to do what, and then you just plug into the equation, and it just evolve, and then just visualize. So here we want to estimate the number operator A dagger A and SM dagger SM. This is for sum of sigma plus and sigma minus. So I can just sigma minus is related to the sigma z. Sigma minus sigma plus. And so we evaluate S dagger times SM. So that's the product of the two. So 0, 1. So basically, it's evaluating what's the occupation of this level. Okay, so this is the output. I think that's used the recommended keyword, right? And it's soft, like very quick. You plot that. So what we are plotting is we plot the first expectation, that's the number. Okay, out of the label cavity, and the expectation 1 is atom excited state. So it start with the first diagonal element and measure what's the probability still stay there. Okay. Right. Okay. So you see that initially atom is in the excited states and sort of oscillate, but has some decay. And you have a cavity which has no photon. It's vacuum in the beginning, and then as the atom decay, it emit photons, but the cavity is leaky, so then photon get out of the cavity and still decay. So eventually, the atom will be in the ground state, and the cavity will probably have no photon. Okay, this is at 0 temperature. So what about we have final temperature? This is setting the average number of photons to there, and then this is the same formula we had before, and solve this. Okay, yeah, let's change this to the recommended keyword. Yeah, and you see the trend is still like that, right? And cavity is also oscillating, but because there's a finite temperature, so cavity would not decay to 0, and the atom will also not decay to 0. You see this asymptotic, it probably is somewhere here, 0.2 something, because there is a thermal photon there. So you decay to ground state, but you also get excited by the thermal photon. Okay. Yeah. So this is the notebook, right? It took us maybe just 5 to 10 minutes. Okay. So maybe let me continue for 5 minutes. So I uploaded all these photon bursts that maybe let's go to this one because this is from a paper. This is actually a program to reproduce some of the results in this paper. Quantum jumps of light, recording the birth and death of a photon in cavity. This Nature paper, 2007. Okay. And the solver we're going to use will be the Monte Carlo solver. So my goal is to show you a different solver. But maybe we won't have time to discuss the physics too much. So this is quantum jump of light, recording the birth and death of a photon in the cavity. Okay, so let's import the basic things. Set up the system, right? So the system very simple. Just A dagger A. And there's one photon in the cavity. We truncate up to 5, actually four photons, up to 4 photons, including the vacuum. Okay. You set the jump operator or collapse operator with A and A dagger. Then you do the Monte Carlo simulation. Oh yeah, allowed a individual realization of the system. So this is like you take a photon and then sort of follow its dynamics as a jump discretely. Okay. Yeah. So in contrast to the master equation solver, which solve for the ensemble and so you're averaging over. So this Monte Carlo solver allow you to observe the trajectory. So it says over advantage over many runs of identical system setup by passing the number of trajectory to the function. If you choose n equal to 1, then you are following 1. So it'd be 1. And then if you have 2, then you see the 2 different trajectory. You can then it average that. So the more, it's like you were doing the simulation of shots in our discrete quantum computer. But this is like a system evolving, observing that and doing discrete jump, and then you average many things, and over the ensemble, that would be the same as the master equation. Okay, so we set up different trajectory number, 1, 5, 15, 900, and we collect the result. We set the time from 0 to 0.8. And for each number of trajectories, we use MC solve. And you see it's identical. H, initial state, list of time, C, the jump operator, the operator list for you to do expectation value. The additional thing is this n trajectory. N trajectory is equal to this n. And you find the result and show that, okay, it's running. It's really sampling. Future, I thought I used that. Oh no, here I did not use that. But let me not run this again. Okay. So you reproduce the plot. We are showing the plot here, and we plot expectation value 0, which is the A dagger A, which is number of photon. And let's plot that. This for one in different trajectory. This will be trajectory 1, right? And trajectory 5 is averaging. So you see there's a jump here, right? It's not vertical because of discrete time. So this time instance, next time instance, I drop to the ground state, this vacuum. And this 5 averaging of that, and right, it's decay, is reproduced as you have like 900 trajectory. So this is using Monte Carlo simulation and allow us to keep track of trajectory, which I think is a great tool. And even there's an experiment that observed this single jump. And earlier I mentioned this block red field solver, right? You see this, and when we talk about Lamor equation, it does not rely on one specific approximation. There's no need for the secular approximation. So let's see, does it provide some comparison? Yeah, so there will be let's see the solver, and yeah, so it will be ME solve, right? And also the BRME solve. Right. So there will be some comparison. So I'm just going through this notebook quickly. This will be the last notebook I'm going through. So the Hamiltonian is sigma z, the simplest one. And we define a dissipation to the environment. It's 0.25 for the gamma. This epsilon is the energy. And you have 100 points in time. And setting up this Hamiltonian, right? E over 2, initial state. This is the initial state similar to what we have seen previously here in Lamor-precession. This is the state we start with. and you set up the jump operator, collapse operator, and this is the E operator. So let's use the keywords so they won't complain. Okay, and then you solve it. This is for ME solve. So still master equation, then master equation. We already seen the result. And yeah, for this QuTiP BRME solve, we have to give the interaction of the system with the bath as a mission operator together with a noise power spectrum, which define the strength of interaction for frequency. Okay, so I'm not going to explain what is. So, but basically we define a constant interaction whenever the frequency is positive and no dissipation for the negative frequency. So it allows us to use sigma x instead of this non-emission sigma minus. Okay, so this up here using this lambda function. W is the, for example, what it says about the frequency. If it's positive, then you have this operator. Okay. So I mean, you can print this. This operator is on an object. For example, this is the corner object that has this, but there is a implicit as a frequency that you can set. Okay, instead of C up here, you pass this A up to the Bloch-Redfield master equation. To solve that, that's also use the keyword. And you compare the two. Essentially, there's not much difference in this particular case. Okay, this storing state, okay, instead of expectation, you could also use state. If your input of the operator for expectation value is empty, and you can evaluate and then plot, for example, sigma x. You plot that. There's not much difference between the two methods. You could also animate. You can also animate that. There's an animation of how the state evolve. So let me not go over this red field tensor. There's more information probably here. Bloch-Redfield mass equation. There is a tensor there. So yeah, so that's not worry about this. Yeah, if you are doing research in this, you probably dig out later. Yeah, so let me open the notebook to see if there is a difference that between the two different solver. I've seen a notebook that somehow show that. This is cavity 3D. Yeah, so there's one case that we have this coupling of the light to the atoms. If you use MESOLVE and VR MESOLVE, there's a difference. The example of a single qubit is too simple to illustrate the difference, but with the field, then there is some difference. Actually, it gets bigger and bigger as you go increasing in time. So this is the number of atoms in the cavity. You see dramatic difference at time about 10, right? And also number of the atom, the response, right? It's visible. So yeah, so I am not going to go through this. But it's interesting that they show different regimes, no coupling weak, strong, and you could test, right? So I guess I will probably stop here. Any questions? So this is the end of this. And there's a few, there are more of QuTiP you can explore. So QuTiP is more of a traditional software from quantum optics. And then with the quantum circuit, they add these QuTiP underlying QIP package.